Okay. Hello, everyone. It's about 1 o'clock, and so we'll get started here. My name is once again Aaron Dobos, and this is a NREL SAM webinar on modeling a residential photovoltaic system. The presentation today will consider all the steps needed to model a solar photovoltaic system for a residential house using the System Advisor model. We're going to cover things like downloading solar resource data from the NREL radiation database, designing the PV system, downloading electricity rate data from the utility rate database, updating incentive information, working with building load data, and interpreting the results. A couple announcements before we get into the material. First, next week at the same time, there will be a follow-on webinar where we're going to extend the material in today's webinar by adding a battery system to the mix. My colleague, Nit Diorio, will be leading that. Please register for that webinar. Registration is free, but space is limited. And you can get more details on the learning page of the SAM website listed below. And for your information, this session will be recorded and posted on our website after the webinar is over. The presentation slides and the associated SAM project files will also be made available. During the webinar, if you have any questions, you can enter them into the chat window or the questions box in the GoToWebinar user interface. My colleagues Janine, Nick, and Paul will be monitoring those questions as they come in and offering responses. There may be time for some question and answers at the end of the webinar. So a quick overview of SAM. SAM is free software for modeling the performance and economics of renewable energy projects. This project has been developed at NREL. It's funded by DOE. It's been around for about 10 years. Currently, we make versions available for Windows, Mac OS, and Linux. And we release 1 or 2 new versions a year with new features. Occasionally, we make some patches to fix some bugs. And those can be automatically downloaded to your computer. We also offer a software development kit for those of you who are programmers or are interested in using the SAM calculations in your own software. There's ways to do that. We also have webinars on that, recorded webinars on that posted on the SAM website. And as far as support goes, we have a very extensive help system. So nearly 1,000 pages if you were to print it all out. So, so that's a lot. Probably better not to print it. We have lots of documents on our website. We have technical manuals. There's an online support forum. And there's also a contact form on the website to send an email to us directly. So in today's webinar, we're going to go to the very pretty state of Oregon. And we're going to look at modeling a 3.3 kilowatt PV system. So this system, here's a little Google Images screen capture of the rooftop of the system. So you can see 12 panels there, some trees off to the east. And so we're going to just go through all the steps that you would need to do in SAM to model this system. Of course, sometimes when you're using SAM, you may not have you may be doing a feasibility study, and so you're not going to be using specific components or other things. But in this case, we'll just use this as an example on how to use SAM for PV modeling. So the bulk of this presentation will be a live demo of how to do that. On the previous page, I showed some information about the PV modules and inverter, and here's some other information that we're just going to assume for the modeling exercise. You don't need to remember all of this. I'll bring it up as needed as we go through the process. So next, I'm going to switch over to SAM and get started. So I'll open up the System Advisor model. We'll let it fill our screen. So before we even get started with the new project, I'd like to point out where the help system is. On the main page, there's a button called Help Contents, and you can click that. And up pops a new window where you can see all of the various topics that you can get help on. Of course, SAM does a lot more than just PV modeling. So there's CSP models, linear Fresnel models, but for this webinar, we'll be focusing on just the PV model. There's there are direct links here to the website, the forum, email support, release notes, as well as you can get information about the particular version of SAM that you're using, just to be sure that you're always up to date with the most recent revisions. Okay, so to get started, we'll click the Start a New Project button. Here you can select from the various models that SAM has. There are two photovoltaic models in SAM. There's a detailed model, which is what we'll be using today, and there's also the PV watts model, which you may be familiar with online. So the pvwatts.nrel.gov website uses the exact same model as the PV watts option in SAM. And if you're familiar with it, it's a pretty simple model and it's quite easy to use. There's only a handful of inputs that you really need to use it effectively. And so we make that option available in SAM too. But for today, like I said, we'll be using the detailed model. The main difference with the detailed model is that you can select specific components, such as modules and inverters, and you have far more options for choosing how those components are modeled. Once you've selected a performance model, you can choose from the available financial models. You can model large systems in SAM too, residential or commercial systems. For today, we'll pick the residential distributed generation financial model. Click OK, and here you'll see the main SAM user interface. A SAM project file can have multiple cases in it, and each case is shown on this tab list at the top of the screen. The first thing I'm going to do is go into the case menu and using the little down arrow next to the untitled, and I'm going to rename this case. So we'll call it a 3.3 kilowatt system in Beaverton, Oregon. Okay? And you'll see that case name get populated up there. On the left, you see all of these, we call it the navigation bar, and it's the way to navigate through all the input pages that you might need to visit to model the system in SAM. So the first page by default that you see here is the solar resource page. There are many ways to get solar resource data into SAM. The first option is to use the National Solar Radiation Database. This is NREL's flagship solar irradiance data product. You can visit the NSRDB website by clicking that link, and it'll pop up here. You can get more information about the type of data that's available, but it basically covers the continental US, Mexico, top of South America, and also, and it covers that space at a 4-kilometer grid cell. So there's a lot of details you can get about that, but for now, what we'll do is just click the download button and type in the address or coordinates of the place that you're looking to model. So I'm going to type in Beaverton, Oregon, and click OK, and go out to the website. You can download multiple years of data, so you can download data from 1998 all the way up to most recently 2014, or you can work with TMY files. TMY is a typical meteorological year file and is done by post-processing all of the specific year data into a data set that is representative, that is typical of conditions at that site, but is not a specific year. So for our work, we might as well pick 2013, which is when the system that we're looking at was, I think, is when it was installed. So we'll click OK, and then hopefully, if all goes well, it'll download some data and tells you that it was successfully downloaded. And it'll also add it to this big list of weather files. When you download SAM from the website, about 1,600 data files are included in the download, and you can search them here if you want. But and then when you download a weather file from the NSRDB, it adds it to the database and selects it here. If you want to get more information about the weather data that you downloaded, you can always use the View Data button in SAM, which will pop up a window where you can look at all the details of the various data sets, of all the various data columns that you downloaded. Irradiance data, temperature data, wind speed, and all these other things that SAM uses. If the weather resource data page doesn't include data that works for this particular site you're looking at, you can also visit the data website where we have some resources for finding primarily international weather data. There's also a summary of the different types of weather data, information about the file formats, and basically just a really good reference for anything having to do with weather and irradiance data. So going back to SAM, we've already selected Beaverton, Oregon, so we'll just proceed from here. The next step is to select the photovoltaic that you're going to use in the system. Looking at this list here, you can see that there are lots of different ways you can calculate the performance of a PV module. In this webinar, we're not going to go into the details about the differences between those, only to say that the default option, the CEC performance model with the module database, is the most straightforward one to use and is fairly accurate. So if we recall back to the slide that we saw earlier, we know that these are solar world modules. So I'm going to search the list by typing in solar world, and then I'm going to select the solar world 275 watt monocrystalline module. When I click that, that selects the module and applies all the information from the same database about that module into the inputs, and it updates this current voltage curve. You can also see the nominal efficiency, maximum power, and other characteristics about that module. Since we selected the module database option, all we need to do is just click the module in the list, and we're done with this input page. There are some advanced options you can look at later, but we're not going to talk about those today. Next, we'll select an inverter for the system. Once again, there are multiple ways of calculating inverter output. There's the CEC, which is the California Energy Commission database of inverters, or there's ways that you can enter information about inverters from a data sheet or using measured efficiency data. So we'll stay with the database option. I'm going to select the SMA. I guess there's already an SMA one selected, but the one that I want is a little bit smaller. It's the 3000, so 3 kilowatt inverter from 2013, 240 volts. So it's a fairly new inverter, a little bit smaller than the default one, but it's a fairly high, 96 or so % efficiency. Once again, selecting the inverter in the list is all you need to do. Everything else on this page is just information from the database. So the next input page here is the system design. Here's where it can get a little bit more complicated. There are two ways to design a system in SAM. You can either specify a desired array size, and SAM will calculate the number of modules and inverters that it thinks it needs to get as close to that desired system size as it can. Or you can specify the electrical layout by telling SAM the number of modules per string and the number of strings in parallel, as well as the number of inverters in the system. So we're going to use the complicated option, or, well, the specify modules and inverters option. And although everything looks fine, I'm actually going to go ahead and change the wiring layout. The reason is that in general, you want the module string max power voltage, that's VMP, this number here, the 193.8 number, to be somewhere in between the maximum power MPPT voltage input ranges for the inverter. And although it is right now, it's very much on the bottom end of the MPPT range. So that could result during the year in some amount of clipping. And so I'm going to redesign the system. I'm going to keep 12 modules, but I'm going to put them all in one string. So if I put in 12 modules per string, one string in parallel, then we have the same 3.3 kilowatt system, but the string max power voltage is 387 volts, which is more reasonable given the voltage range of the inverter. We also see that the DC to AC ratio, which is the size of the DC system, which is 3.3 kilowatts, to the AC size, which is the 3 kilowatt inverter, is 1.1. 1.1 is a reasonable number. Some systems might have higher or lower DC to AC ratios. Okay, now that we've laid out the electrical connection in the system, the next thing to do is to select the orientation. Since this is a rooftop mounted system, we're going to select a fixed system. You can also do 1-axis, 2-axis, or azimuth axis tracking systems in SAM. And because the roof tilt in that picture that I showed looks fairly small, we're just going to enter a tilt of 15 degrees. Because the panels are pointing southeast, looking at this azimuth diagram, we'll set the azimuth to be 135 degrees, which represents a southeast pointing system. Okay, so that's all I need to do on this page. If you have a more complicated system that has multiple subarrays, which would mean that you might have a set of panels that are facing east, or a set, in addition to a set of panels that face south, you could set up multiple subarrays to represent each subsection of your system. But for this, we have a single system, single contiguous array of PV modules. On the next input page, we'll look at shading and snow. This is where we get into entering information about various losses that your system might experience due to the environment that it's in. There are multiple ways of entering shading losses. Shading might come from trees or other houses nearby your system. The primary place to enter shading information are these shade loss tables. And since I only have one subarray, that's the only button that's enabled here. So I'll click Edit Shading. And if you've taken images of the sky using a SunEye device or a solar pathfinder device, or if you have an installer that you're working with, or if you are an installer, you may be familiar with those. But those are ways to measure the shading at a proposed site and import that data into SAM. If you've used PVSys before, you can also import information from PVSys. Or if you have other ways of calculating shading losses, there's a number of ways you can enter that information into SAM. I'm not going to go through all the details here, but we'll reserve a detailed discussion for a future webinar on shading alone. There's also a 3D shading calculator that you can use in SAM to mock up a scene using 3D geometry. And if there's time at the end of the webinar, we'll come back to that and take a look and see what that looks like. But for now, we'll assume that there's no shading on our system. And The input boxes down below here are for self-shading. If you have multiple rows back to back, then one row can shade the next row. And so for large systems, SAM has a feature to be able to calculate that type of shading. We don't have that in this system, so we'll leave those inputs alone. In locations that experience snowfall, snow can obviously reduce the power output of your system quite a bit. So there's a model to estimate losses due to snow coverage, and all you need to do to enable that is click Estimate Losses Due to Snow. If the weather file has no snow data, as this one doesn't, the simulation will fail. So since I don't have snow data in the weather file that I'm using, I'm just going to turn off that option. On the next input page, we're going to look at other losses that might impact the system. These are primarily losses that aren't modeled, that don't have real robust equations behind them. So they're really just for you to enter information about what you think is appropriate. For example, you can enter loss from soiling, so dirt falling on your system. And the default value in SAM is about 5%. You could have a monthly variation in that if you know that during rainy months there might be less soiling, but that's very site-specific, and so for this exercise we'll just leave the defaults alone. There are also losses that you can enter for module mismatch, wiring, tracking error, and all these other categories. For the time being, we're just going to leave the default options. If you know you're using a special type of inverter called a microinverter or a DC optimizer, you can use one of these buttons to reset the default loss assumptions to make them more appropriate to the type of inverter that you're using. Since we're using that SMA string inverter, I'll make sure to use the defaults for the string inverter case. On the next input page, you can enter the degradation of modules. In the default mode, SAM will calculate the hourly output for your PV system in the first year, and then degrade that total annual output each year in the financial model. So this 5% per year, or half a percent per year, means that every year in the financial model calculation, the PV system performance will be degraded by 0.5%. On the next page, you see the battery storage option. I'm not going to go into this here. That will be the topic of next week's webinar. So please register for that, and you'll get a lot more information about how to model battery storage systems from my colleague, Nick. Moving on to system costs. So at this point, we've filled in all the information about the PV system design, selected modules, inverters, and designed the system. From all the following input pages from here on out are all having to do with costs, financials, and incentives. So the first one is the system cost page. We have default costs that are representative but not specific to any particular system by default in SAM. So if you don't know what the cost of your system will be, it's okay to start with the default values. I, for whatever reason, think that these modules are going to be a little bit more expensive. So I'm going to change the PV module cost to $1 a watt. That brought up my total installed capacity to $3.40 a watt DC installed. So this is like a little spreadsheet. You can work with your costs and see what the total cost of the system is. There are also operation and maintenance costs. So these are costs that have to do with keeping the system running over its lifetime. I'm going to enter a cost to replace the inverter after 10 years. I'm going to assume that for whatever reason, and after 10 years, my inverter breaks and the warranty for some reason isn't going to help me out. So I'm going to enter a cost for that. The way to do that is look in this fixed annual cost option, and this is a little hard to see, I assume, but there, if you click this blue-gray thing here, you can switch the mode of this input from a single value, dollars per year, or to a schedule where it turns into a button, and you can enter a schedule of costs. So in year 10, I'm going to enter a $1,000 cost for replacing the inverter. And I'm going to click OK here. We'll see that impact in the results after we do the simulation. And these are just sort of guess numbers. They're not real costs, and an inverter warranty might cover you. And so this is just a representative exercise to show how you can enter this kind of information into SAM. Okay. So leaving costs aside, we'll move on to the financial parameters. The first thing I'm going to do is switch to a standard loan, and that means that the PV system is not part of a mortgage, so the interest payments on the PV system are not tax deductible. And this assumes that the customer or the homeowner owns the system and pays cash for it. If you want to do a financial model that looks like if you were leasing a system from a provider, then there's another financial model called the third-party ownership model that you might be more interested in for lease type arrangements. Okay, so just for the sake of changing defaults, I'm going to say that we're in a low inflation environment and change the inflation rate just down to 2%. And then I don't really know what the state income tax rate is in Oregon, so let's ask Google. And let's see, google.com, what the state tax rate in Oregon? Question mark. Oh, good. So it's somewhere between 5 and 9.9%. Since I'm not going to find out more information about that, we'll just type in 8%. Good. We'll take a similar approach on the next input page when we have to consider incentives. So there's a lot of ways you can enter incentives into SAM. There's investment tax credits, investment-based incentives, capacity-based incentives, production-based incentives, and all of this is all of these different types of incentives have a lot of information on them in the help system. So if I just click the help button up here, up pops the window, and there's a lot of information here to help you sort out what all of this means. Okay, so starting out, let's assume that there's a 30% investment tax credit from the federal government, and not knowing anything about Oregon, let's assume that there's no state investment tax credit. Of course, we can also go to this desire, which is the database of state incentives for renewables and energy efficiency. So this is an organization that collects information about incentives. So let's go to their website and type in the zip code, which I happen to know is 97008 for where we are in Beaverton, Oregon. And here's a long list of all types of incentives that may or may not be applicable to the system that you're looking at. There's special incentives for low-income households. There's tax credit information. But the one that I'm going to use in our demonstration is the Solar Electric Incentive Program. So I'm going to click on that, which is the fourth one on the list. And wow, this was updated very recently, August 12th. That's great. So let's scroll down. So this is an incentive for solar photovoltaics from the Energy Trust of Oregon. Okay. So residential PGE incentives. So since in our case we're customer owned, so we're owning the PV system, there's a 50 cents a watt DC incentive. So let's take that information and add it to SAM. Going by the units, it was a 50 cents per watt, or half $1 a watt, and we'll type that in. Let's call it a state incentive, even though I think it's probably other. I'm not sure how the Energy Trust of Oregon is categorized, but for now, let's just put in the 50 cents a watt in capacity-based incentive into our inputs. Okay, I think that wraps up our discussion of incentives. So let's move on to the electricity rates. This is a fairly daunting set of inputs, but we don't have to really spend a ton of time to understand all of them at this point. SAM can model very complex utility rate structures. It can do time of use rates, tiered rates, demand charges, time of use tiered rates, and all sorts of other charges and different units with different metering structures. And so once again, I would very much advise people using this to consult the online help system. But luckily, there's an online database for utility rate information called the NREL URDB. So I can go to that website here, and this is on the Open Energy Information portal. So you can get information about utility rate structures from this database. SAM has a direct linkage to that database, so you can just click the Search for Rates button. And sometimes it takes a little long to get all the information, but luckily it happened quickly this time. So I'm going to search for PGE, Portland General Electric, and select that. And here's a list of all the rates that have been entered into the database for PGE. Absent better knowledge, I'm just going to pick the first one, which appears to be a time of use, TOU rate. I can click download and apply, and then it tells me that it was applied successfully. So if I scroll down again, I can see that all of this information with the rate structure has been entered. These are actually editable boxes here. You could change the rate information that you downloaded just by highlighting a block of cells and typing a number. So I changed that to 3. I'm going to change it back to what it was, 2. Just to illustrate that these are all editable, and you can tailor the rate. If you're doing research on electric rates, you can use this structure to look at the impact on economics of different rate structures on PV systems. There are also different metering options of whether monthly excess generation is rolled over in kilowatt hours to the next month, or in dollars, or if there's no rollover. There's also a 2-meter option. So these all attempt to model different types of structures that might be used by a utility to calculate your energy bill. Okay, so the final piece to successfully modeling a residential PV system for a behind-the-meter type application is that we need an estimate of the electric load. And that's necessary to be able to put a number on the value of the PV system in terms of how much it reduces the amount of electricity you would need to buy from the grid to meet your load. And once again, we have this nice drop-down list at the top that gives you options for entering load data. So if you have your own load data, you can enter it here. It's hourly, or you can enter sub-hourly load data if you have it. But for my case, I don't have load data for this house. So we have a simple electric load estimator that you can select by clicking Calculate Electric Load Data. And this is a really simple model of a residential home that estimates the profile, so the hour-to-hour change in load as a function of temperature and heating and cooling loads that you might have in a home, but it's calibrated to the total monthly load data that you enter. So this you might get from a utility bill. But let's go through some of these inputs one by one. For the house that we're looking at, let's say it's about 1,700 square feet. I happen to know that this home was built in 1984. It is one story, so we'll enter that. And we don't know how many people there are, but let's say there are 2 people living in this home. And they like it a little bit colder. So let's set the heating set point to 64, 72 for the cooling, 64 for the setback, and 72 for the cooling setup. Okay, so those are the basic parameters. And since I don't really know what their monthly load data is, I'm just going to say it's 500 kilowatt hours a month during the spring. Let's say it jumps up to 800 kilowatt hours a month through the summer, assuming there's air conditioning, and then back down to 500. Okay, so having entered some basic parameters about the house, I can click this View Load Data button, and that'll go off and run the very simple load model and present the estimated hourly load profile for the home. What's nice about this and what's really important about it is that it's using the weather file that you selected on the solar resource data page up here at the beginning of our webinar, so that the temperatures and the cycling of the air conditioning and things like that, they're all coincident with the temperatures and irradiance, that data that you're using to model the PV system. So I keep everything consistent. Okay, now that all the inputs are filled in, let's save the project file before we proceed. Here we go, and I'll just do PV system in Beaverton. Always a good idea to save your work. So now, having entered all the inputs, let's click the Simulate button. SAM goes off and runs the hourly simulation and the financial model that you selected, and presents you with a whole series of outputs. And we'll spend some time here looking at some of these outputs just so that people are aware of all the ways you can look at the results. On the summary page, there's information about some key metrics. Of course, the total annual energy produced by the system, the capacity factor, LCOE, net present value. It's negative in this case, which means that this may not be a great investment, but there's potentially several reasons for that. Looking at the monthly energy production, of course we have more production in the summer months with higher irradiance. Looking at the cash flow here, you can see that in the first year you got those incentive dollars that went into the system, so that's a positive in your cash flow. Of course, remember we had a inverter replacement in year 10 for $1,000, and so that's where you see this negative spike in year 10, and that's showing the cost of replacing the inverter. Moving on from the summary page, there's a losses page that you can see here. You can scroll down this, and it shows basically where the losses in the PV system are and how it gets from the total available solar irradiance down to the energy that's coming out of the inverter. I'm going to skip a couple tabs here. The next one we'll look at is the data tab. And here is where you can get all the numerical outputs from SAM. So I'm going to start by looking at some of the electricity rate data by year. And let's look at the utility bill with the system and without the system. So here's, so down the, all the rows are the various years in the simulation split out by month. So you can see the utility bill with the system and compare it to without the system. You can send this data to Excel if you want, and it'll pop up that data that you selected as various sheets in Excel. And so you can then go and do further processing of that data if you wish, create custom graphs or whatever you want with it. You can also look at monthly data. So you can, let's see, what are we going to look at? Perhaps maybe system AC energy. And you can get a month-by-month breakout of that data. You can also look at the hourly data, and there's lots of things to look at here. So let's not pick anything in particular for now, just to know that all of that is available. On the next tab, there's the cash flow. You can see all 25 years of the financial simulation. Each year there's the energy production that's getting smaller due to the system degradation. The value of the electricity savings in each year. This is because SAM runs the utility bill calculator based on the complex utility rate with the load, and then, or with the load only, and then with the load and the PV system to determine the net benefit of having added the PV system to your house. And then all the details about incentives and taxes and stuff down there. You can use the same sort of time series data viewer to look at the electricity load here. This is the same data that we showed on the previous slide. So you can zoom in by selecting a field. You can also display the system power. So this is the PV production overlaid with the load here. You can also show the available solar irradiance on a second set of axes. And so you can really dig into the details and scroll through the year to see how the system is performing. You can look at average daily profiles for each month on the Profiles tab. For example, this is what the solar irradiance looks like on all of these tabs. Okay, so that's a good start to browsing all the results. One thing that might be a useful feature if you want to file away several versions of reports is to create a report using from the case menu here. You can select Create Report, and Sam will update the simulation results, and I'll save it as a PDF file. Save that. And then if I go to my desktop, I can open that up in a PDF browser. And there's a three-page summary of most of the key inputs, some of the key outputs, and the losses from your PV system. So this is a report that you can save and file away in addition to the project file, of course. Okay. That pretty much brings me to the conclusion of the key things I want to convey about modeling a PV system in SAM. Just as a teaser for a future webinar, I want to go back to the shading and snow page and give you a quick insight into the 3D shading calculator. Before I do that, let's look back at the results just to see what the total annual energy is. 3,437 kilowatt hours. That's, of course, without shading. So I go back to the shading and snow page, and I open the 3D shade calculator. I'll click OK. And it brings up a dialog here. I don't have time right now to build the 3D model on the fly, so I'm going to import a 3D scene that I created before the webinar. Okay, so here's an image, the same image of the house with the roof and the PV system and two of the big trees that are in front of the house. If I go into the 3D scene view, this is what it looks like in the 3D view we were looking at the bird's eye view, where you can also have an elevations view. All of these objects are editable, so you can click and point and drag and change the 3D scene right here. You can go to the Analyze button and click a quick diurnal analysis, which will show average shading losses at the time as a function of the time of day and month of the year. So you can see that there's some shading in the morning hours, which makes sense due to those trees being to the east. And so to include this information in SAM, I'm just going to click Save and Close, and it'll update the shade loss calculations. And then I will click Yes, update the time series shading and diffuse losses for Subarray 1. So I've clicked that button. Then I can, if I go into this Edit Shading table option again, I can see that the 3D shading calculator filled in all of the detailed information about the shading losses at each moment in the year. So if I go and simulate that system again with those 3D shading losses being entered, it'll simulate again, and you see now it's only 3,159 kilowatt hours. So maybe I don't know, 5 to 10% loss due to shading on this particular system. Like I mentioned, I hope that in the future we'll be able to do a whole webinar on just going into the various shading options in SAM and giving a little bit more information, as that is definitely one of the key considerations for residential PV systems, managing trees and shade. Typically you'd like to put the panels in the sun, but that's not always possible. And so with the remaining 10 minutes, I think we can try to address any of the questions that may have come in through the chat window or the questions box that haven't already been answered by my colleagues, or if there are other questions, then I think we can potentially open the floor to people to ask their questions over the phone. So are there any, Paul, Nick, and Janine, are there any questions worthy of immediate verbal reply?
Let us dig back through. We've had a lot of questions that we've been answering as we go through. So for people who are on the webinar, you can also view the questions and answers that have been asked by others in the team as we go through, and we'll dig back through and see if there are a couple to highlight. It also may be worth mentioning again the battery webinar.
Thank you, Janine. Yes, I'll put the information for the battery webinar back up on the presentation, so please do register for that. I'm sure it'll be interesting for figuring out how energy storage might impact any of these questions that we've dealt with today.
There were a chunk of questions on finding weather data for international sites. Perhaps you could show that page.
Sure. So weather data for international sites is a question we get a lot. If you go to the location and resource page, there are about 360 locations, cities, that we've included typical meteorological year data for. For example, if I look in China, there's a handful of weather stations in China included in SAM. There's, if you want to look in Australia, there's a couple there. So you can browse the existing typical year files that are included in SAM. And once again, I'd point out the SAM weather data website. Here's, again, lots of information about global weather data sets. There are private companies like Solar GIS and Meteonorm that provide solar resource data that's compatible with SAM. SAM's weather file format is a very simple text file. So, for example, I can open the folder where these files are, and they're just CSV files. So you can open this weather data file in Excel, and if you have your own weather data file with the data that you need to run SAM, you can create your own CSV file in Excel. Much difficulty. SAM doesn't even require the columns to be in any particular order, and we have some resources, some documentation on that file format to help you get started. Let's see. The NSRDB also, I would once again mention, does cover Canada, Mexico, parts of South America, and I believe there's a large chunk of Southeast Asia, including India, that's included in the NSRDB. So I think going forward, look, there's a section here about new international data sets, and those are growing. So here's the information about those data sets that is available through the NSRDB. And sorry, that's about all I have to say. Paul, is there anything you would like to add about international weather data?
Just to mention that there are companies that sell the data that are listed on the weather data page of the SAM website, in case you didn't mention that.
That's right. Very good. Thank you.
It might be good to comment on, there were some questions about why the NPV was negative, and if you could comment more on how to interpret that result for this particular case study.
Sure. The way in general that I would interpret that result is that the system is fairly expensive and that there isn't frankly, a lot of energy production for large portions of the year. So the net present value represents sort of a positive net present value would indicate a good investment where you make some money over the lifetime of the system. In this case, with the net present value being negative, it indicates that you're not recouping the cost of the system over its lifetime with the savings that you would get from it. So that could be tied to the fact that the electricity might be really cheap, so the savings aren't very high, which may be true since in Oregon electricity is relatively, I mean, I guess average. I don't really know if it's high or low, but it could also have to do with you might look for greater incentives. We haven't necessarily entered all of the incentives into SAM that might be applicable for this particular system. And also the cost. This might be far too high a cost, especially if it's perhaps a bulk purchase program in which you might get more competitive pricing. So all of these assumptions are really inputs into SAM, and then how those all get parceled out into the outputs is it's a complex interplay between production, solar resource, shading, the electric load estimate, the rate structure, and incentives.
There were a couple of questions on inputting modules and inverters if they aren't in the database. Maybe you could go over one of those pages a little bit more.
Sure.
About 5 minutes remaining.
Yeah, in the 5 minutes remaining, we can revisit the PV module input pages. So the questions were about how would you work with a module that may not be in the database. So for that, the first place I would start is the CEC performance model with user-entered specifications. So this is the exact same PV performance model as the database option, except that you can take information from a module data sheet, enter it here, and use that information to run the simulation. So if I were to click Calculate and Plot, so suppose I've gone and gotten a data sheet, entered these 10 or so parameters from the data sheet. If I calculate and plot, I'll get the IV curve, that the current voltage characteristic that SAM uses to model the module's performance. So that's one way to enter information about a module. If you are using a module that may not actually physically exist yet, in the sense that it might be a research grade module or a cell, of which you may only know its efficiency or some sort of generic behavior. You could use our simple efficiency module model, in which you have a set of parameters that define the module response or module's conversion efficiency at different levels of irradiance, how much of the diffuse irradiance it can accept, and you can use that. If you have a lot of test data, according to a standard for PV module testing called IEC 61853, you can go into the IEC 61853 module model option, enter a bunch of test data, which I'm not going to go into here, but then calculate parameters for a module that fits that information to a bunch of equations at various temperatures and irradiances. So this is probably one of the most complex ways of entering data, but you do need a fair amount of test data to be entered into the tool to make it work. And finally, there's also the Sandia PV array performance module model option. This one comes with a module database, but the database is not updated as frequently because the parameters that go into this model require significant module testing also. So that's a very quick summary of the different module model options. And I think we have time for one more question. Janine?
It seemed like there was a lot of questions that some of Sam's more advanced features could probably answer. So maybe you could quickly mention just what those features are and where people can see webinars on those features.
Yeah, thank you. That's a great question. So what I showed is basically just the interactive SAM user interface, but that's not the only way to use SAM. So suppose you want to figure out what the best tilt angle is for a location. You can use the parametric analysis and enter the tilt, choose different values of it, and you can run a batch simulation of maybe 10 different tilt angles. I'm not going to go and actually set this up right now. It takes a moment, but just to mention that you can set up a set of simulations with 20 tilt angles, 20 different degradation rates, and look at the variation of LCOE, excuse me, or annual energy as a function of those different inputs. There's also a stochastic simulation option, which you can assign distributions, probability distributions, to various inputs in the model. And Sam will run a Monte Carlo simulation to figure out what the distribution might look like for the outputs. There's also a P50, P90 analysis, which is an exceedance probability analysis, which for 30 years of weather data, for example, you could figure out what the likelihood is that your annual energy production will exceed a certain value. There's also some built-in macros for using SAM. For example, you can create a sensitivity plot or a tornado chart using this macro. And finally, there's also scripting. And if you're familiar with Excel, and you can write some fairly straightforward scripts, you can automate all of SAM in code using if statements and for loops and save results to disk and change all the inputs in SAM using programming code. So there's a lot of ways to extend the built-in functionality of SAM, which brings me to the end of the webinar at 2 o'clock. I think I would like to point out in the last couple seconds a few things on the website. We have all of our previous webinars recorded on our videos page, and there you'll see webinars on scripting, on parametric and statistical analysis, third-party ownership financial models, anyways, a whole host of information about different ways and you can use SAM. Once again, I'd like to thank you very much for your attention today and your participation. Please do register for next week's webinar, and from all of us at NREL, we hope you enjoy using SAM in your PV system simulations. Have a very nice afternoon. Thank you.